Okay, welcome to AP Chemistry, and our first video for this course is going to be a review of the summer assignment. It was optional, but many of you have asked me questions about specific problems, and so I'm going to discuss the assignment with you. It was about 4 pages long, and I don't want to make a really long video, so I'll just discuss pages 1 and 2 in the first video, and then pages 3 and 4 in the second. The first page has solubility rules and nomenclature practice. And so the first part is a review of the solubility rules, which they're identical to the ones that we had in honors chemistry last year. They're necessary for college chemistry, but they are not supposedly specifically tested on this year's AP exam. Remember that the AP exam, AP Chem exam has undergone some significant changes. However, I'm going to expect you to know and to be able to apply these solubility rules. Something else you should know is that depending on which textbook you use in college, it may have different solubility rules than those that we've used in this course. And so just be aware that there might be some variation, especially with calcium hydroxide and a couple of other compounds. But I'll point those out to you as we get to them. Okay, the next part of the first page had polyatomic ions that you should memorize, that you should know. A lot of these are ones that we used in honors last year. The ones with the blue dots are those that are probably fairly new to you, and we may not see them very often. So I just think that you should recognize the name or recognize that it's a polyatomic, and then know where to go look for the correct formula or the correct name, depending on what it is that you're trying to answer. All right, next we have common formulas and charges for some common ions. Notice that most of these are transition metals. There are a couple of exceptions here. You should know just by looking at aluminum on the periodic table that it always carries a +3 charge. The second one is hydrogen. When it's carrying a negative charge, it's called hydride. You'll find those at the end when hydrogen is the second element listed in a binary compound. Additionally, you should know that nickel carries a +2 charge, and zinc carries a +2 charge, and silver carries a +1 charge. So those are the 3 common transition metals that we see in this course that don't have charges that vary. Cadmium carries a +2 charge, but we don't use that a whole lot in problems that we work. The rest of these are common transition metals, and you should know that if gold carries a +1 charge, we call it gold 1, and if it carries a +3 charge, we call it gold 3. These Roman numerals are called the stock system of naming, and it's much easier than the old way of naming that used ic and us endings. Okay, then we had some naming practice, and so what I've done is I've just written out the answers for you to save myself some time on the subscripts. I just wrote them by hand, so I'll go ahead and clarify in case my handwriting isn't really neat. This is a 4, that's a 4, that's a 4, that's a 2, 2, 2, 2, 2. Okay, and then over here we have the names. And you should be able to correct those. If you need to pause the video to check your answers, you can do so. I'll move on. Okay, and then the rest of the naming, again, 2, 3, 4. Led to acetate, so you're going to have 2 carbons, 3 hydrogens, 2 oxygens, and then a subscript of 2 behind the parentheses. This is a 4, 2, 2, 4, 3, 2, 3, 2, 3, 3, 2, 2. Okay. And then over here you have the names again. I put stars beside things that I wanted you to name as acids. Remember that acids will generally start with a hydrogen. There are 2 types of acids. You have binary acids and you have oxyacids. Write some of this out for you. So binary acids will just have a hydrogen and then one other element. It doesn't have to be in a 1-to-1 ratio. Let's just take W for example, hydrofluoric acid. It'll always start with the word part hydro, and then it'll have the root name of the element present. It'll end with ic, and then acid. Okay. Binary acids, those are in contrast to your oxy acids, and as the name would indicate, those contain oxygen. So if we come up here to look at letter O, the way that we name oxy acids, you find the name of the polyatomic present, and so in this case you should recognize that C2H3O2- is called acetate, and if it ends in an 8, the 8s become ics, so that's how it becomes acetic acid. Whereas on the previous page we had HNO2. You should recognize that NO2 is called nitrite, and if it ends in an ite, it becomes an us, so this becomes nitrous acid. Okay, so there's a little review there of your binary and your oxy acids. Then I asked you to remember the 6 strong acids. The definition of a strong acid is something where the proton or the hydrogen ionizes or dissociates completely from the other atom that it's bonded to. And so for hydrochloric acid, it would dissociate completely, which means you're going to see a one-way arrow here into the hydrogen ion and the chloride ion. So we have hydrochloric, hydrobromic, hydroiodic. These 3 are your binary oxy acid, or your binary acids. And then down here, the last 3, nitric, perchloric, and sulfuric, those are going to be your oxy acids. Now, I asked you to consider why hydrofluoric isn't considered a strong acid, and you should recognize that because fluorine is the most electronegative element, it doesn't let go of hydrogen to a degree of 100% that we see in the other strong acids. And so because it doesn't dissociate completely, it's not a strong acid. Okay, next we had some stoichiometry to work here, and this was finding the mass percent of nitrogen in each of these. I'm not going to work all of them out for you, but I will give you the answers. So let's look at A first. We have nitrogen monoxide, and the way that I taught you to find mass percent in honors is to write out all of the elements that are present. So we have nitrogen and oxygen here. Then count up how many atoms of each you have. We have 1 nitrogen and 1 oxygen. Then multiply that number of atoms by the average atomic mass of that element. For nitrogen, we generally use 14.01. So 1 times 14.01 is 14.01 grams, assuming that we have a mole of it. And then oxygen is going to be 16.00. So altogether, we get 30.01 grams. Now, it wants you to just find nitrogen, but I'm going to show you nitrogen and oxygen for both of these. For nitrogen, 14.01 grams out of the total 30.01 grams is a little bit less than half, so we should expect a number slightly less than 50%, and we get something like 46.68%. Notice that I've gone to 4 sig figs here because I used 2 digits past the decimal, which is fairly commonplace when we're doing calculations. All right, oxygen, on the other hand, weighs 16.00 grams out of the 30.01 grams, so that's slightly more than 1/2, and you get something like 53.32%. When you're doing these, remember that they should add up to 100%. If you get something, like 99.99, you're probably okay. It had something to do with rounding, but if you're off by more than, a 100th or so, or 200ths either way, I'd say go back and check. All right, so there you have it there. In B, I'll go ahead and just give you the answer here. Nitrogen should be 30.45%, and oxygen is 69.55%. In C, nitrogen is 30.45%, and oxygen is 69.55%. Well, hold the phone here. What do you notice is similar between B and C? Well, look, we have the same percent by mass. Why is that? Well, when you look at the ratio of nitrogens to oxygens in each compound, you'll see that they're the same. In this case, we have a 1:2 ratio of nitrogens to oxygens. Over here, we have a 2:4 ratio, which of course reduces to 1:2. And so because we have the same ratio, we're going to have the same percent by mass. So remember to use your noggin as you're working these problems. Lastly, D, nitrogen is going to be finally greater than 50%, 63.65%, whereas oxygen is going to be 36.35%. Okay, so hopefully you don't have any questions on those, but just remember to count correctly and to make sure that you're multiplying by the correct average atomic mass. Okay, next we get to a empirical formula and molecular formula problem. We have benzene, which is a very common organic compound, and it tells us that it contains only carbon and hydrogen. So we know at this point that the formula is CXHY. No oxygens, no nitrogens, anything like that. It also tells us that the molar mass of the compound is 78.1 grams per mole. That's going to be useful when we get to the molecular formula part of this. Analysis shows that the compound is 7.74% hydrogen by mass, which means that the carbon has to be 92.26%, because whatever is not hydrogen has to be carbon, and that's dictated by the fact that it told us that it was only a hydrocarbon compound containing carbon and hydrogen. Now, if you remember, it's telling us here to find the empirical and molecular formulas. The empirical formula rhyme goes something like this. Percent to mass, mass to mole, divide by small, multiply till whole. And so we'll use those 4 steps as we work through this problem. Okay, so we already have the percents, and we want to convert first to mass because it doesn't tell us the entire mass of the compound. What we're going to do is we're going to, since these percents add up to 100%, we can just assume 100 grams, and we'll turn these percents directly into mass by changing the percent to grams. All right, so the next step is to convert from mass to mole. We'll do that by applying the molar mass. 1 mole of hydrogen is 1.008 grams. Okay, because we have 3 sig figs here, we'll carry 3 to our answer. And so if you divide 7.74 by 1.008, you get something like 7.68 moles of hydrogen. Down here with carbon, 1 mole of carbon is 12.011 grams. We have 4 sig figs here and 5 here, so we'll carry 4 to our answer. And we get something like 7.681 moles of carbon. Okay, what do you notice here about these two amounts? They're basically identical, right? Okay, so the next step when we divide by small, technically 7.68 is less than 7.681. So if we divide by 7.68, we get a ratio of 1 here. If we divide by 7.68, we get basically a ratio of 1 here. It's 1.00 something. And so we don't have to do the final step, which is multiply till whole, because these are already whole numbers. So the ratio is a 1-to-1 ratio, which tells us that the empirical formula is simply CH. All right, next we want to figure out what the molecular formula is. It tells us that the molecular formula weighs 78.1 grams per mole. Well, we need to figure out first how much the empirical formula weighs, and then determine by what factor we need to multiply the empirical formula to get to the molecular formula. So the first thing I do is I have students just sort of guesstimate about how much the empirical formula weighs. So 1 carbon weighs about 12 grams, and hydrogen weighs about 1. So altogether, the empirical formula weighs about 13 grams per mole. Now we need to compare the empirical formula to the molecular formula. It tells us that the molecular weighs about 78.1 grams per mole. So how many times does 13 go into 78? Well, 78 divided by 13 gives you about 6 times. So that means that the molecular formula is 6 times what the empirical formula is. Since each of these carbons and hydrogens has a subscript of 1, you're going to multiply that by 6. So the molecular formula is C6H6, which is the correct molecular formula for benzene. Okay. One last problem that I'll do in this video, and then we'll move on to the next bit. Okay, you have a problem here. Calcium carbonate decomposes upon heating, producing calcium oxide and carbon dioxide. The first part is to, of course, always write a balanced chemical equation. So calcium carbonate. I know that calcium carries a 2+ charge, and carbonate is CO3 with a 2- charge. Next, it tells me it decomposes. So a decomposition reaction will generally have one compound that's decomposing. And it tells us it's decomposing upon heating, so you could put your little equilateral triangle above, which means it's heating. And it produces calcium oxide. It's going to be CaO and carbon dioxide, CO2. Next, you'd want to put in state symbols if you know them. In this case, we know that carbon dioxide is a gas, calcium oxide would be a solid, and calcium carbonate is a solid as well. If you don't know those, that's okay. You should at least know that carbon dioxide is a gas. Okay. Next, check to see if it's balanced. 1 calcium, 1 calcium, a carbon, 3 oxygens, 3 oxygens. So we're good here. Okay. Whoop. Next, it gives us the information how many grams of calcium oxide will be produced after 12.25 grams of calcium carbonate are completely decomposed. So you still want to use your balanced reaction. Calcium carbonate decomposes into calcium oxide and carbon dioxide gas. Next thing we need to do is, as we read the problem, I underline what it is I'm trying to find. So we want to know how many grams of calcium oxide, underline this and write how many grams, and then it tells us that we have 12.25 grams of calcium carbonate here, and it tells us that it's completely decomposing. Okay, what is the ratio of calcium carbonate to calcium oxide? Well, obviously it's a 1-to-1 ratio. So 1 mole of this will make 1 mole of this. However, do those moles weigh the same? No. Calcium carbonate is going to be heavier than calcium oxide because this has a carbon and 2 extra oxygens as opposed to the calcium oxide. So first thing we're going to do is start out with 12.25 grams of calcium carbonate. And before you can compare anything, you have to get to moles. So the first step is to say, okay, well, 1 mole of calcium carbonate, if we add all of these things up, equals 100.091 grams. Okay, grams on top, cancel out grams on bottom. Now I'm in moles of calcium carbonate. At this point, I can compare moles to moles using the mole ratio. And so 1 mole of calcium carbonate, so remember that whatever is on top is what you're going to put on bottom, is 1 mole of calcium oxide. That wasn't pretty, but it works. And so now moles of calcium carbonate cancel out. Now we're in moles of calcium, excuse me, calcium oxide. We want to get to grams. So 1 mole of calcium oxide weighs how many grams? If you add that up, it works out to be something like 56.08 grams. Moles of calcium oxide on top cancel out moles of calcium oxide on bottom, and we'll be left with grams of calcium oxide, which is what we're asking for. Remember to multiply across the top and divide across the bottom, and when you work it out, you should get something like 6.864 grams of calcium oxide. And I kept 4 sig figs because that was the original mass given to us here. Remember that when you have a problem, you should have 3 things: a numerical value to the correct number of sig figs, you should have units, and then you should have the substance that you're talking about. Okay, put a box around your final answer. And the last part of the problem says what volume of carbon dioxide could be produced with 12.25 grams of the calcium carbonate at STP. What does STP stand for? Standard temperature and pressure. So again, we need our balanced equation. Calcium carbonate decomposes into calcium oxide and carbon dioxide gas. We want to know how many liters at STP we can make from 12.25 grams of the calcium carbonate. So we're going to start the problem off the same way. We can see obviously that we have a 1-to-1 mole ratio here. But instead of going from mass to mass, this time we're going to go from mass to volume. And the only way we can do that is by comparing moles. So the first thing we have to do is to get our mass of calcium carbonate into moles. So 12.25 grams of calcium carbonate. And the same molar mass as before, 1 mole of calcium carbonate is 100.091 grams. So obviously we only have 12 grams out of 100. We have a very small amount, slightly more than 1/10 of a mole. Okay, grams on top, cancel out grams on bottom. Now we're in moles of calcium carbonate. We can compare to moles of carbon dioxide now. So 1 mole of calcium carbonate produces 1 mole of CO2. Moles of calcium carbonate cancel out. Now we're in moles of CO2. Lastly, we want to get to liters of CO2 at STP. And so perhaps you remember that 1 mole of any gas at STP always equals 22.4 liters. That's part of Avogadro's law. So 1 mole of CO2 is 22.4 liters. That's, of course, at STP, as the problem indicates. Okay, finally, moles of carbon dioxide on top. Cancel out moles of carbon dioxide on bottom. Go ahead and multiply across the top and divide across the bottom, and you should get something like 2.74 liters of CO2 gas at STP. Okay, and so put a box around your final answer, and you're done. Okay, that should be good for the first 2 pages, and stay tuned for the next video.